Section: Introduction. In this section, we discuss the significance of autoregressive (AR) language models, which have greatly advanced sequence generation and achieved top results in various tasks like translation and text summarization. By using the chain rule, we can break down the probability of a sequence into manageable parts, focusing on predicting the next token. This approach makes both training and inference efficient. However, during inference, once we select a token, we cannot change it, which can lead to errors that accumulate over time. Recent improvements in large language models, LLMs, have concentrated on enhancing training through better data, changes to the transformer architecture, and reinforcement learning fine-tuning. Despite these advancements, the actual sampling process has not been thoroughly explored, with many models still using the basic next token prediction (NTP) method. We introduce a new sampling technique called resample previous tokens (RPT), which allows us to revisit a set of previously sampled tokens. Unlike NTP, where once a token is chosen, it cannot be altered, RPT enables us to make local changes during generation, which may help reduce errors. Our RPT training is efficient, allows us to fine-tune existing AR models, and maintains the quality and speed of NTP sampling. We fine-tuned a pre-trained 8 billion parameter AR model for a portion of its training and found that RPT improved performance by 5 to 10% on common benchmarks compared to the fully trained model. Our contributions include 1. Presenting RPT as an effective sampling method. 2. Creating a training algorithm that integrates smoothly into the AR training process with minimal additional cost. And 3. Showing that RPT outperforms standard NTP sampling in reasoning and coding tasks, as well as in error analysis. For RPT sampling, we define a sequence of tokens, where each token comes from a specific vocabulary. AR modeling uses the probability chain rule to understand the joint probability of sequences. Our aim is to minimize the errors associated with NTP sampling by implementing RPT. We start with pairs of adjacent tokens sampled using NTP and perform several iterations to refine our predictions. To apply RPT, we need to learn not only the next token prediction but also the previous token prediction, which helps us predict a token based on prior tokens and a future token. We observe that predicting a token using a future token generally results in lower errors compared to standard NTP, leading to improved sampling outcomes. We will further analyze the errors in both NTP and RPT sampling in the following section. Additionally, we can extend our approach to longer sequences, adjusting the window size for our sampling process. If we set the window size to a specific value, RPT will revert to standard NTP sampling. Section Summary. In this section, we introduce resample previous tokens, RPT, a novel sampling method that allows for local token replacements during generation, thereby reducing error accumulation compared to traditional next token prediction, NTP, sampling. We demonstrate that RPT can be seamlessly integrated into autoregressive models, providing significant improvements in performance on various benchmarks while maintaining efficiency. Section: Learning the conditionals required for RPT. In this section, we focus on learning the conditionals necessary for resample previous tokens, RPT, sampling. For RPT sampling, we need to sample from specific conditionals. To achieve this, we look at two sequences of indices. The first sequence is a rearrangement of the order in which tokens are input into the model. We denote this entire rearranged sequence as a specific term. We only consider a certain type of rearrangement, where a random index is moved a few places to the right. The second sequence indicates the target token index for the model's output. All tokens predict the next token, except for those that specifically predict a past token. During training, we randomly rearrange each training data sequence with a certain probability. This rearrangement is done by sampling from a set. Given the long sequences typically used in text modeling, we often swap more than one token. We start with the original order and move through the indices, moving each index forward by a few places with a certain probability. If we move an index, we continue from the next index to avoid overlaps. To model both the next token prediction, NTP, and the previous token prediction, PTP, conditionals, the model needs to know if the input and predicted tokens have been rearranged. We address this by using a learned positional embedding layer that takes the input and target positions. The model compares the output to the target token using a standard loss function. Next, we analyze the differences in error between RPT and NTP sampling. We start with a simple case of two tokens and denote the true joint distribution of the next two tokens given the context. We perform an asymptotic error analysis, assuming small errors in the approximated conditionals used in both sampling methods. The marginal and conditional represent the NTP, while the previous token prediction represents the PTP. We quantify the errors using total variation distance between the two sampling methods. Under certain conditions, RPT sampling can lead to lower error compared to NTP. We define the RPT factor as the ratio of the error bounds for RPT and NTP. Our main observation is that the PTP error is generally much lower than the NTP errors, suggesting that predicting the next token with knowledge of a future token is easier. To support this empirically, we use Pinsker's inequality to relate total variation distance to KL divergence. We assume that the entropy of the true conditionals is low for non-trivial contexts and large vocabularies, allowing us to focus on cross-entropy comparisons between NTP and PTP. We observe that PTP has a significantly lower cross-entropy loss, indicating lower total variation distance. Finally, we derive asymptotic bounds on the sampling errors for both NTP and RPT and compute the RPT factor, starting with the NTP errors. Section Summary. In this section, we describe the process of learning conditionals for resample previous tokens, RPT, sampling, which involves permuting token sequences to predict the next token based on both current and past tokens. We analyze the error rates of RPT compared to standard next token prediction, NTP, sampling, demonstrating that RPT can achieve lower error bounds due to the inherent advantages of predicting future tokens when given context. Section. Next token prediction asymptotic error. In this section, we discuss the asymptotic errors associated with next token prediction, NTP, and resample previous token, RPT, sampling methods. For NTP, we can calculate the error in predicting the next two tokens using the probability chain rule, where we denote terms that become negligible in comparison to others. When analyzing the error in RPT sampling, we find it requires more complex calculations since it involves the stationary distribution of the RPT process. We can view the RPT iterations as a Markov chain, where the states consist of all possible token pairs. The RPT process can be interpreted as sampling from a specific Markov probability transition kernel, which aligns with a single iteration of our earlier equation. While one part of this process predicts the next token, another part predicts a specific token based on the previous context, leading to a smaller error. Before we estimate the overall error in RPT, we first need to determine the error in the kernel, which we can compute similarly to before. We establish a bound on this kernel error using the maximum norm, and we refer to the appendix for detailed derivation. To bound the RPT sampling error, we apply standard perturbation bounds, where a constant related to the true Markov chain, known as its conditional number, plays a role. There are various definitions for this constant, some more intuitive yet harder to compute than others. A relatively straightforward definition involves the transition matrix of the Markov process and its ergodicity coefficient, which indicates how quickly the influence of the initial state fades over time. By incorporating our kernel error into the relevant equation, we derive the RPT error bound. Comparing this bound to previous ones allows us to identify the RPT factor. Next, we present a synthetic experiment designed to compare NTP and RPT sampling. We created a random ground truth joint distribution with a specified vocabulary size, sampling independently from a uniform distribution and normalizing the results. To introduce noise, we generated a noisy distribution and set specific noise levels for different conditions. We examined 3 noise scenarios: oracle, medium, and low, and computed the sampling errors for both NTP and RPT across 1,000 repetitions. The results, shown in histograms, indicate that the smaller the ratio of noise levels, the greater the advantage of RPT over NTP, with RPT showing significant improvements even at moderate noise levels. In terms of related work, we note that autoregressive models typically use NTP sampling, which is based on the chain rule of probabilities. However, NTP has limitations, as it cannot correct previously predicted tokens, leading to potential error propagation. Previous research has attempted to navigate the model's probability space using methods like beam search, but these approaches face practical challenges such as repetition and collapse. Our work builds on traditional NTP sampling by introducing RPT, a new method that enhances sampling from the joint probability of tokens. Section Summary. In this section, we analyze the asymptotic errors in next token prediction, NTP, and resample previous token, RPT, sampling methods, highlighting that RPT, modeled as a Markov chain, can correct previous token predictions and reduce error propagation compared to NTP. We also present a synthetic experiment demonstrating that RPT outperforms NTP, especially in scenarios with higher noise levels. Section: Predictor Corrector. In this section, we discuss the predictor corrector approach. Discrete diffusion models often remask previously revealed tokens, but these techniques do not directly apply to autoregressive language models, LLMs. Instead, some researchers suggest prompting the model to self-correct using carefully crafted inputs. Other methods modify the model's architecture or generation process to achieve similar outcomes, such as introducing a predictor corrector mechanism that allows for state accumulation and enables the insertion, deletion, and replacement of tokens during generation, effectively performing implicit correction iterations. While previous studies have made notable advancements, they have not reached state-of-the-art performance. We propose new training and sampling procedures that facilitate corrector iterations for LLMs, enhancing the current state-of-the-art. Next, we introduce any-order architectures. Our method enhances standard next token prediction by incorporating explicit information about the permutations of input and target tokens. Previous research has looked into any-order language modeling, proposing architectures that use double positional embeddings to represent the absolute positions of both observed and target tokens. They also achieve permutation awareness by altering the attention bias. In contrast, our sampler only requires local permutation awareness within a window of size 38 and uses non-permuted targets. This approach necessitates a small embedding table that encodes the relative order of the 38 most recent context tokens. This straightforward addition maintains the traditional next token prediction loss while requiring only a slight adjustment to the training process. In our experiments, we evaluate the performance of our resample previous token, RPT, method. First, we show that RPT sampling can be trained with minimal fine-tuning of a pre-trained next token prediction model while preserving its performance. Second, we conduct an error analysis comparing RPT to traditional next token prediction sampling, demonstrating improvements in the total variation distance of learned conditional probabilities, as partially predicted by our theoretical framework. Finally, we test RPT sampling on code generation and reasoning benchmarks, showing enhancements in both RPT pre-training and sampling. Our data comprises a corpus of 1 trillion language tokens. Throughout our experiments, we use the same training dataset and maintain the same data order. We pre-trained an autoregressive model with 8 billion parameters using standard cross-entropy loss on this 1 trillion token dataset for 240,000 iterations, which we refer to as our baseline, ARF. We denote the checkpoint after 224,000 iterations as ARC. We then fine-tuned ARC to reach 240,000 iterations using the remaining 100 billion tokens, corresponding to 10% of the total training tokens, with specific iterations and hyperparameters that align with our expected swaps in each sequence. Our method also requires information on whether the predicted token is permuted. To include this information, we introduce a learned positional embedding layer. One approach is to learn this layer for the source target pair, but this would involve global positional encoding. Instead, inspired by relative positional encoding, we encode the source target pair relatively by using their difference as input to the learned positional embedding layer. For practical sampling, we focus on a specific window size as we did not observe significant benefits from using a larger, more computationally demanding window size. A key advantage of RPT sampling algorithms is their ability to incorporate various sampling heuristics not typically available in standard autoregressive sampling. We tested two useful heuristics, greedy decoding and a confidence threshold for accepting tokens. In our main paper, we consistently use greedy decoding and provide additional analysis on this approach in the appendix. Section Summary. In this section, we propose a novel predictor-corrector mechanism for autoregressive language models that enhances performance through improved training and sampling procedures, allowing for implicit corrector iterations. Additionally, we introduce a method that incorporates local permutation awareness in token generation, maintaining the conventional next token prediction loss while requiring minimal modifications to the training pipeline. Section: Evaluation. In this section, we first confirm that our fine-tuning process does not harm the NTP sampling performance. We present the autoregressive training loss for 900 billion tokens and the fine-tuning phase, where we further train our method with an additional 100 billion tokens. We notice that the NTP error follows a similar trend, showing a slightly higher NTP loss at convergence, which is minor compared to the cross-entropy loss. Meanwhile, the PTP losses quickly drop to much lower error values than the NTP loss, as we predicted in our theoretical analysis. Essentially, using more future tokens for next token prediction leads to better results. In our coding results, we demonstrate that NTP sampling with our fine-tuned model often scores better on benchmarks than our autoregressive baseline at convergence, suggesting that our fine-tuning may enhance the model's performance. For error analysis, we calculate the empirical total variation distance between the conditional probabilities from RPT and the actual distribution represented by the ground truth token in a validation set. We report these distances using 128,000 validation set tokens from various datasets, all with a context of at least 20 tokens. The RPT error shows that the predicted probability of the ground truth token decreases significantly after the first RPT iteration and continues to decrease moderately afterward, consistent across all validation datasets. Our theoretical analysis discusses the error in the limit case, which appears to stabilize after just a few iterations with our sampling method. We compare the probabilities assigned to ground truth tokens by RPT and the NTP sampling process, showing that RPT improves the probability of the ground truth token in 64.5% of cases, indicating better sampling properties for RPT compared to NTP. We evaluate our method on well-known coding and reasoning benchmarks, including Human Eval Plus, MBPP, GSM-8K, and Multi-PLE. Our results summarize the performance of RPT sampling against NTP across several baselines. We include results from our fully trained AR model using NTP sampling and from the initial fine-tuning checkpoint for direct comparison. Our findings consistently show significant performance improvements with RPT sampling compared to the NTP baseline across all benchmarks. We report results with confidence sampling and provide additional ablation results for non-confidence and non-greedy sampling in the appendix. For a fair comparison, we also report oracle scores over various temperatures.